Hello and welcome to this video about vector spaces. In this video I'll step through some difficult proofs that you'd find in linear algebra so as to make them more understandable, since nothing is usually done to help the reader to understand them. I'm starting a new course on displaying some of the most difficult proofs in this subject. I'll take it for granted that you are familiar with a lot of the concepts in linear algebra, but still have difficulty reading and understanding the proofs. So I'll focus on the proofs. I'll start with these 6 theorems that are considered to be the most difficult. The notations help make them difficult because the notations can be clumsy, so I'll try to clear up clumsy notations. I've already done a video on these proofs, but I'd like to redo them because they were still a bit too confusing. So we'll start by defining some vectors. This is the standard vector u used in these proofs. It's usually a column vector with n entries, so it can have any number of entries, and is written with an arrow on top, which is how vectors are written these days. I've also written them in colour to make them stand out from the scalars and other math symbols that surround them. And the first change I'll make is to call the 0 vector 0 and not z. It'll be coloured with blue with an arrow on top to distinguish it from the number 0. And it will be a column vector with the same amount of entries as vector u. All of these entries will be 0. This is its main property, that when it is added to another vector, then the value is unchanged. This is its definition. And I'll define its negative to be u written with a superscripted minus sign, which is used in high school when introducing students to negative numbers, rather than using a big minus sign, which could be confusing. This vector will be a row vector like u, but it will have all its entries being the opposite of the entries of u. And this is its main property. Adding it to u will give 0. I've used n in a previous video, but I felt it was confusing, since it was a function of u. So now for the first theorem, that there is only one 0 in a vector space. I'm following the theorems in a textbook that I bought years ago, rather than numbering them myself. So to prove this theorem we have to start with 2 zeros. I've chosen theta to be my second 0 because it looks enough like 0 to help the viewer to see it as being a 0, but not too much like 0 like the letter O, which makes it look indistinguishable from 0, and not too different like A or B, for example. And then we're required to prove that these 2 zeros are equal. This is enough to show that there really is only one 0. So the first step is to start with the first 0 and add the other 0 to it, because it's a property of a 0. Students are used to simplifying expressions and not expanding them to add an extra 0 to the end, but it's alright to do it in a proof, since the aim is to prove something and not to find the answer to a question. And then we can eliminate the first 0, because the first 0 has this property too, and so we're left with the second 0. So there you have it. We have a chain of equal signs showing that these 2 zeros are equal, and it was done in only 2 steps. And now for the second theorem, that each vector has only one negative. The proof will be similar to the last one. We'll start off with 2 negatives, and then show that they are equal. I've decided to use the letter n for negative that I used last time, since there really isn't anything better to use. I gave these vectors similar colours. So here's the first step. We'll start off with the first negative of u and expand it out by adding a 0 onto the end. We'll be doing this a lot, which is an act of desimplifying the expression. Then we can expand out the 0, which is also an act of desimplifying the expression. We've got to be careful to put these 2 vectors the correct way around in these brackets, because we want to eventually get the first 2 vectors in this expression to cancel out. So now we come to this axiom, which allows us to swap the brackets. I know that it's obvious, but it can't just be done obviously. We can only do this if these objects are in a vector space, or in a similar structure. We can then simplify the first bracket, because it's a property of a negative added to its positive to give 0. This time we're using it in the forwards direction that most people are used to using it in. And then finally we can eliminate the 0 because it's a property of 0. So there we have it. There's a long chain of 6 expressions all being equal to each other, proving that these two negatives are equal to each other. So now to prove this theorem. It looks painfully obvious, but it isn't really. The definition of 0 means that when it is added to a number, then the number remains unchanged. This definition doesn't automatically extend to mean that multiplying a number by 0 gives 0 back again, so we have to prove it. We'll start from the left-hand side and try to make it equal to the right-hand side. We'll desimplify it by adding a 0 to it. This is a legitimate step to use in a proof. Then we can expand the 0 by making it equal to a positive vector added to its negative. These will be in brackets because this addition is done first in this expression. Then we'll use associativity to swap the brackets. It can obviously be done, but we need to use an axiom. Then we can use the property of 1 to put a 1 in front of this vector. We can then use distributivity to factorize this expression. Then we can add these two scalars in the brackets because they aren't vectors, and we can add them together like any real or complex numbers. Then we can simplify the first vector to eliminate the 1 using the property of 1 in the forwards direction. And then finally we can add these two vectors together to make 0 because one of them is the negative of the other. So we have a chain of equalities that make 0 multiplied by a vector equal to the 0 vector. So this proof is universal and can be used for any vector space. Now for this next theorem that is similar to the last one, only this time it's a non-zero scalar multiplied by the 0 vector. We'll need to use a vector u, even though it's not shown in the statement of the theorem. So now to start the proof, we'll start with the left-hand side, and we'll substitute this expression in for the 0 vector. This is the first time that we've used the previous theorem to prove a new theorem in this video. Theorems can and do build on each other like this. Now we'll use associativity to swap the brackets. It's multiplication this time. This multiplication by 0 is a property of scalars that we don't have to prove here. And so we can use the same past theorem again in the forward direction this time. And so this theorem is proven true. And now to prove this obvious theorem, that multiplying a vector by -1 gives its negative. The opposite or negative of a number is defined to be the number that when added to its positive gives 0. This multiplication by -1 is an extra property that has to be proven. And so we'll start with the left-hand side and add a 0 onto it, which is a property of 0. Then we'll expand the 0 out into a pair of positive and negative vectors, chosen to eventually cancel the first vector in this sum. Then we'll perform this bracket swap, which has to be shown, and have an axiom or theorem given for it. Every small change in the expression has to be accounted for. We'll use the property of 1 to place a 1 in front of the vector here. Then we'll factorize this part of the expression. These two numbers in front of the vector can be added together to make 0. We can then use this theorem a third time to perform this step. And finally we can use the property of 0 to eliminate the 0 vector, which completes the proof. And this is the final theorem. It says that if the product of a scalar and a vector is 0, then one of the two must be equal to 0. We can do this by cases. In the first case, we'll consider when a isn't 0. Then we can use this theorem to expand this 0 vector out like this. This is the second theorem that we've used in another theorem. We can use the fact that a has an inverse because it isn't 0. We can expand the 0 vector out like this because it's given in the statement of the theorem. Then we can gather the scalars together into the same bracket. And two scalars multiplied together give the number 1, when 1 is the inverse of the other. And we can use the property of 1 to eliminate the 1, so we're left with this theorem being proven for the first case. And then we can do the next case when a is equal to 0. Well, that satisfies the theorem. I thought I'd mention it because I felt that it wasn't quite obvious enough and needs to be mentioned in this proof. So I hope that you found this video to be helpful and insightful. Please click like and subscribe if you did. Please leave some helpful thoughts in the comments. Feel free to share this video, and thanks a lot for watching.